So far we've talked about spectroscopy, especially as it relates to absorption and emission. I've left fluorescence till last, and that's partly because fluorescence is absorption followed by emission. Laser-induced fluorescence is absorption followed by emission. And interestingly enough, we're going to find out that the fluorescence in many ways is simpler to deal with than the absorption, except for one or two problems that we'll talk about. So there's 3 lectures today, 13, 14, 15. I hope this is not unlucky 13 for you or me. A little bit of history, typical setup, and which will help motivate why we like fluorescence. We'll deal with signal levels so you can understand where that comes from. Introduce the simplest fluorescence model, the 2-level model, which turns out to be just about enough most of the time, very simple. We'll talk about detection limits, which will help you understand why fluorescence is so popular. Talk about characteristic time so that we'll understand the times over which the key assumption that we use, which is called the steady state assumption, holds. And then we'll talk about some potential modifications to the 2-level model that you might run into in some circumstances. That's this hour. So what is laser-induced fluorescence? It's really laser-induced spontaneous emission. It's a multi-step process. It's absorption followed by emission. So you go from one state to another with a photon that matches the energy difference of an allowed quantum transition. And then subsequently, at some period of time, there may be an emission of light. So the molecule is here, it has options. One option is to undergo a transfer to another rotational state, another state. And along the way, as it moves around in this state, it'll have a chance to emit light. And that would be laser-induced emission or laser-induced fluorescence. Now, this helps me make the point that the emission could come from different places. It doesn't necessarily come from 2. It might come from adjacent states. It may come from 2. So whereas this goes between only 2 specific states, which we might have picked using our understanding of absorption, the fluorescence can come from different places. Therefore, it's not an instantaneous process. So whereas we might think about absorption as being essentially an instantaneous process, the fluorescence is not. There might be a time delay that we have to think about. Why do we care about laser-induced fluorescence? Well, it's sensitive, but it also, for people interested in fluid mechanics, has a huge advantage, which is that it provides a way to make spatially resolved measurements. So typically, there's some sort of a laser beam that might be focused to what's called a waist, or you could think of it as being collimated, and the light that's emitted by fluorescence goes out into 4 pi stair radians. But we have to collect that with a lens, and the lens will have some sort of an F number or collection angle, and then that light goes to a detector. That means that the signal that you're looking at comes from a small region of space that corresponds to the overlapping volumes of the illumination optics and the collection optics. So assuming there's not any competing radiation from elsewhere in the collection of this lens, the signal comes from what we'll call a point. A point could be small, could be big, but that means, and it doesn't have to be 90 degrees, but it typically is. So that means that there's a mechanism to make a spatially resolved measurement, which you might want if you're studying a flow that's spatially non-uniform. Now this is going to come at a price, and you'll see what the price is. But this is a huge advantage for certain situations where you really want to study the spatial structure of the flow. Now another nice thing about fluorescence is that the signal rides on a dark background. That is, presumably if you've blocked all the emission, you see nothing until you induce this pulse from the laser. So that means that you have basically a detector with a minimum signal, and then you see a blip, and then it goes away again. So you're seeing the difference against a dark or low signal background, which is in contrast with absorption, where we're measuring the difference against a strong signal. We have to measure the difference between I0 and I. And here we have an advantage, but again, it comes at a price. Now, let's see. This is a plot of wavelength here. So whereas we might imagine our absorption line, the thing to keep in mind is that the emission line, the fluorescence line, if it comes from that same state back to the origin, is just going to have the same spectral character. That turns out to be an issue at some point. All right, so I'm going to give you a bit of an introduction. It's going to last for 4 or 5 slides, I think. And I'm going to tell you that we're attracted to this for gas dynamics because there are strategies that we've developed over the years, we and others, that you can measure number densities in specific quantum states. You can measure temperature. You can measure species concentrations or mole fraction. You can measure pressure from line broadening. You can measure velocity from the Doppler shift. So the nice thing about this method is there are strategies for applying laser-induced fluorescence, sometimes called LIF, to measure gas dynamic properties at a point, at an instant in time if you use a pulse laser. So that's pretty attractive. A variety of species have been measured. Diatomic radicals here that happen to occur in flames, stable diatoms that are of interest to us, oxygen, NOCO, and many other polyatomics. Let's see, have I left off? I've left off formaldehyde. Formaldehyde is a pretty popular one, CH2O, for measurements in engines. You'll see people doing imaging of formaldehyde and OH together, trying to benefit from that combined knowledge. So lots of species are available. Now, but the first step is absorption. So you're only going to get fluorescence if you have absorption. So that's something to keep in mind. And there's many atoms. Lots of atomic work has been done with fluorescence. In fact, the earliest work with fluorescence was really done by analytical chemists trying to measure trace levels of atoms, like, say, arsenic in water or something. They would put them in a flame and see if they could see the spectrum of arsenic. So here's our absorption process. So we have levels 1 and 2 of the same species optically for an allowed transition. This would be essentially instantaneous, single step, line of sight, and we usually try to compare the incident and transmitted radiation intensities through Beer's law to get what we're after. Fluorescence, by contrast, happens a little bit later. It could emit from this state back to here, or maybe even to another state, but it might also, especially if it's a molecule, have a collision and go to a different rotational state before it emits, if it's going to emit. What does that mean? That means that the wavelength is likely to be different than the wavelength here. And that actually turns out to be important too, because this fluorescence is a weak process, and your detector may not be able to discriminate between this wavelength and this wavelength, and so you have to block that light somehow. And so that shift in wavelength turns out to be a way of avoiding the problem of competition from your laser source on the detector. So typically it's at 90 degrees, typically it rises on a dark background if you've designed it right. You can do this with either a CW or a pulse laser, although it's much more common to use a pulse laser. Why? Because you get an intense burst of photons. You need a lot of photons in order to get enough photons out. So if you use a pulse laser, you're sending in more photons at a short period of time than if you use a CW laser. Okay, I'm going to give you a little history as far as I remember it or know about it. And this is partly related to how have lasers developed over time. The laser was first developed around 1960, 61. One of the first tunable lasers was a flash lamp pumped dye laser. So in order to dye means that the lasing medium was a liquid dye using a jet, although an initial one sometimes in a cuvette. You have to excite that that laser material up into an excited state. You have to send in energy in some form. It was fairly common to use flash lamps, so you'd have some sort of a pulse discharge of a flash lamp, sends in radiation. That radiation kicks the dye up into an excited state. The dye wants to re-emit at different wavelengths typically. And you put that into a cavity, make some adjustments, and out comes laser light. So it's a stepped process. You've got to send in electricity, convert that to a flash lamp, excite the dye, capture some of that emission into a laser cavity, So in the end, it may not be a very efficient process, but it's very high quality photons, valuable photons. But you can also use a tunable CW dye laser. We have done at Stanford for quite a long time. Now, once these dye lasers were available, they were mostly invisible, but then people learned that they could double their dye lasers. They could take the light and put it through, the light that came out of the visible laser, put it through a crystal, a nonlinear process, and out comes light of half the wavelength or twice the photon energy. So that's called frequency conversion. And we learned how to do this with a ring dye laser in 1980. That turned out to be important because that's how we went from the visible down to 300 nanometers where we could measure OH. Very common to use a neodymium YAG, yttrium aluminum garnet laser, or excimer laser to pump the dye laser. So maybe you use flash lamp pumped neodymium YAG laser to excite the dye laser, which then might be frequency converted. So there's lots of ways to kind of shift the wavelength to where you want it to be. And let's see, also in the 80s, we found a way at Stanford to have a rapidly tuned CW dye laser that was unique then and probably still now. So the extension from LIF to PLIF, planar laser-induced fluorescence, occurred 1981 or so. We published this on the cover of Applied Optics, and I think it was probably January of 82 or so. So it's almost exactly 30 years old. Over time, there were some advances. There's one of my students who made the first measurement in a spray flame. So this happened to be, you're seeing the scattered light and the luminosity of the spray flame. In this background monitor is the single-shot image of OH in this spray flame. So spray flames are tricky because the light is scattered by the droplets, and you have to be careful that that doesn't contaminate your signal. So that was an advance. That was 1986, I would say. So the first one was around 82. We went to turbulent flames in 84 or so. We learned how to get to, and most of this early work was done with OH, or sodium turned out to be really an easy one. NO, temperature, velocity. We were trying to find ways to extend this to different parameters like velocity in the late 80s. These were all mostly combustion generated species except for NO that we would feed in or rely on the combustion generated NO. We got interested in trying to do things the fluid mechanics people would like and identify some tracers that you could do non-reactive, you could use in non-reactive flows. That happened about 1991. And then we got interested in supersonic flows, high pressure flows. Oh, and then this one. Is there anybody here from Cornell? Okay. So my student, who is now professor at Cornell, figured out a way to do this in the infrared. Usually it's in the ultraviolet and it's electronic transitions. But if you think about it, and I'll talk about it a little later, I think that's probably in the next hour. There's a way to do this in the infrared. Now, lately people have gotten interested in trying to do all of this at high speeds, and there's a pulse burst laser that was developed at Princeton and Ohio State, and people are now trying to do what was, the YAG lasers run at say 10 hertz or 20 hertz. Excimer lasers maybe can run somewhat faster, but people have learned how to make their pump lasers go faster up to kilohertz now. Those are expensive, but it's possible now to do PLIF at kilohertz rates, maybe 5 kilohertz rates, maybe 10 kilohertz. We've learned that sometimes we get some surprises, and when you're looking in the UV, we found that CO2 would fluoresce and absorb light, and that was not expected. It turns out to be a high temperature phenomenon. So there's a lot of interest now in going to high speeds. We've been working on this and others, and one clever thing we've done is with a CW laser, so we can go at arbitrary speeds. So that's a quick historical record. So this would be a typical setup. You have a laser. The beam is usually expanding somewhat. You focus it down to a waist or narrow spot through the flame or flow of interest. Maybe you trap this light over here so that it doesn't bang around in the laboratory. You collect this light with a lens, and that lens will have a focal length. It'll have a collection solid angle omega, diameter d, and then you're going to focus that onto a detector of some kind, which might be a photomultiplier with a filter. It might be a spectrograph of some kind, grading monochromator. But this light is going out into 4 pi star radians. So you may only capture 1% of all the light that's being emitted, and you can see that you have to get this lens pretty close to get the solid angle up. So you need a big diameter, big collection angle, which means small f number lens. So this idea doesn't scale very well for something huge. It scales better when you have to keep omega up, omega over 4 pi up in order to get the signal that you want. There's different ways to do these experiments. You could measure at a fixed detection wavelength and just measure the intensity. You could scan the spectrum of emitted light. That would be done with a spectrometer. So you might do that by repeating the experiment and scanning your monochromator, or you might capture that light on a CCD array and a spectrometer. So there's questions about whether you would look at a narrow wavelength that might be different than your excitation wavelength, or whether you want to collect the spectrum of light. You learn different things from different strategies. That's called fluorescence spectrum. So when you capture or pay attention to the spectrum of the fluorescence, that's called the fluorescence spectrum. If, on the other hand, you're more interested in scanning the laser and then seeing what you get, that's called an excitation spectrum. Different strategies. If you have a pulse laser, it's over in perhaps 10 nanoseconds, but the fluorescence might live for a while. And that decay rate contains useful information. So there's a lot of things to look at. Do we care about the decay rate? Do we care about the integral? Do we care about the peak value? Do we spectrally resolve the emission or not? A lot of different options. And some people care about this temporal behavior. So you'll begin to see how these options are used in different experiments. So if you're interested in how big this point is, you have to pay attention to the size of this measurement volume. Obviously, if the volume size is 0, you get no signal. So the bigger the volume and the more photons you send in, and the bigger the solid angle, the bigger your signal is going to be. Let's see. An important issue is the solid angle of collection. So the way solid angle is defined is it's the area, cross-sectional area of this lens divided by L squared, which is the distance from the focal point. So that's essentially 1 over what's called the F number. So when people say, I want a small F number lens, that's why. They want to be able to collect a big solid angle that's going to increase the fraction. So omega over 4 pi is the fraction of the emitted light that you are going to try to collect. If you had an F number of 2.5 lens, which is a reasonable lens, you're going to collect approximately 1% of the light. So pretty fast, you know, if your F number gets big, pretty fast, you're not collecting very much light of that available. Okay, so that's a consideration. So, we talked before that we excite this state. So we know that if there's no collisions, this will re-emit with an average time, which is 1 over the Einstein A coefficient. So in the absence of collisions, and if there were only two energy levels, that's what would happen. But of course, there are collisions. And so some of these molecules, maybe most of them, are going to be atoms or molecules, are going to be returned to this state because of a collision. It's called a quenching collision. It quenches the radiation. So you pump up here. If there's no collision, it stays there until it emits. If there's a collision, it's an exothermic process, so it has usually a high efficiency that it will take that excited atom or molecule back home at some rate. And if that's so-called gas kinetic, it might be 10 to the 10th per second. So now let's look at the signal. Right now we're kind of mostly talking about 2 levels, and you'll see how far we can go with this. So what's the signal? The photons, let's count photons per second of collected light. So it's going to be equal to the number, this is the N2 is the number of molecules in the measurement volume. So I'm not yet telling you how big that measurement volume is. So it would be the number density times the size of the measurement volume. So that's the number of molecules in the measurement volume in state 2, N sub 2. This would be the number density in state 2, number per unit volume. That's the volume. So the product of these two would give you N2. But your signal depends on the absolute number of molecules you're looking at, the probability per second of emission, so this is photons per second, times the fraction of the emitted photons you collect. So that's your signal. Photons per second, in the absence of any optical losses, is the number of emitters, probability per second, fraction collected. Or in terms of number density in V, here it is. Now, where's the laser intensity? It's got to be there somewhere. Well, it's buried in N2. How did you get N2? By going from 1 to 2. Ah, now that depends on laser intensity. So the signal, it's easy to write this equation. Or you can, if you want to do this in terms of power and not just number of photons, you can add the energy of the photon, which would be h nu. So the signal in photons per second times h nu is then the power, because it's energy per unit time. Power, so if you care about power. So interestingly, the signal that you're measuring depends really only on some constants and N2. So if you know the volume, and if you know A, and you know omega over 4 pi, we're almost done. Except that N2 is not so easy to define. That's the problem. Yes?
Professor, do you have to consider transient solution if the laser short course is very short?
I don't. Do I have to consider the transient solution? Well, there's two answers to this. If by transient you mean times less than a nanosecond, yes. If by transient you mean times longer than a nanosecond or two, no. It gets the process gets much more complicated if you have to deal with times that are so short that we have to worry about oscillations. That's called, they have to use a different strategy. This is going to be a rate equation analysis that holds as long as we're able to use steady state. For time shorter than that, you have to deal with this at a much higher level. You usually want to avoid that problem. That's a density matrix, it's called, solution. To be avoided unless you're really interested in that aspect. So it looks pretty good at this point. Now, if we have a pulse of light, which we typically do, we get photons here. Now, and we want to capture the total number of photons, we just have to integrate over time. So now we have to monitor N2 of time dt. So if we just send in a burst of photons and we capture bursts of photons out, allowing the collection to extend over a long enough period of time, it still looked like a pretty simple equation, except now I maybe need to, if I want to interpret this, I need N2 of time. Obviously, this must somehow depend upon the laser and the process, but we haven't had to address that yet. Now we address it, and we do it with the Einstein Theory, which we talked about before. We now imagine, right now, two levels, and later I'm going to show you that even though there's a lot of levels, you can get almost everything you need to know from this two-level idea. Level 1, level 2. And so now we have a possibility of going from here to here by absorption or by emission. This would have been the B12. This is the B21. You're going to see down here, I probably got the definition for W somewhere. Q stands for quenching, that's collisional term. You can either excite or decay. So Q12 means you're going from 1 to 2. Q21 means you're going 2 to 1. And here's the fluorescence signal A. So before, we did not have these two. We left the collisions out. Now we're going to be more thorough. We have to be. So this is really the absorption term, the induced emission term, the fluorescence term, the emission term. What did Einstein theory tell us? The probability, and we can do this in a small frequency interval of nu to nu plus d nu within this line right now. Probability of going, if you were a molecule here, the probability per molecule per second of doing this is this Einstein coefficient B12 times the energy density, but I quickly substitute that in terms of spectral intensity of my laser, times the line shape function d nu. So depending on the width of d nu, that's the fraction of the integrated area, which is one line I have. So this is the Einstein theory gives me probability per second of this happening, and it's linearly proportional to the intensity. But now it's making some sense. It's quite similar to what we did before. I like to quickly substitute my B12 for Einstein's B12 which had these funny units. He did it before the laser, so he did it with photon density, photons per unit volume. So I don't want to do that. I'm going to just use this intensity. So we're assuming illumination of a collimated beam here. So now we recognize that the lasers are spectrally broad. So let's assume then that the laser is kind of broad, and that the intensity, I nu, which is watts per square centimeter per unit frequency, is uniform across the line. So that I nu is a constant. Okay, here's my example. So let's imagine that the intensity distribution of the laser is wider than my absorption line. Why do I do this? So I don't have to talk about the absorption line shape right now. If I had a narrow laser at the center of this line, I'd have to pay attention to the line shape. So now the rate per unit volume of molecules going from here to here would be the number density in the absorbing state times this probability here integrated over the line, and over that interval I want to hold I nu constant. And when I do that, I get this nice simple result. So N1 W12 is the rate, that's the number per second that undergo this transition. And as soon as you see a little n, that means number per unit volume. So that's the rate that individual molecules go, and then the number per unit volume I multiply by N1. So it's kind of like our Einstein analysis, except we're going to now have to pay attention to some of the other processes. So so for times for which we can use steady state analyses, which will turn out to be times longer than, say, 1/10 of a nanosecond or so, we can write the rate equation for N2 as the positive term and the negative term. So you populate by illumination of a laser the number density in 1, and this then is the probability per second that the molecules or atoms go up, minus the loss terms, which are the induced emission, the collisional quenching, and the spontaneous emission, which we actually care about. That's our signal. I've neglected the collisional excitation term because usually this is such a hard thing to happen that you just forget it. It's not a very important term. So now we have the time rate of change of N2 in terms of, and now what do you know about W12 and W21? What do I know about B12 and B21? They're related by the degeneracies. G1 B12 equals G2 B21. Whenever you know, if you're ever given B12, you already know B21. They're related by the ratio of the degeneracy. So remember, if you know the Einstein coefficient, if you know one Einstein coefficient, I can calculate the other two. They're all related. Give me one of them and I can give you all three. I happen to like A because it has simple units, seconds to the minus 1. So that's seconds to the minus 1. Seconds to the minus 1. This term is seconds to the minus 1. That's the term we write as W21. So the W has units of seconds to the minus 1. It's a rate. This is the rate equation for N2 in terms of the positive and the negative terms. And what do we do when we invoke a steady state argument? We say that the time rate of change of N2 is small compared to the magnitude of these two terms. So we'll set it equal to 0. That is, we'll set the left-hand side equal to 0. Then you can solve for N2. So that N2 steady state is given by this simple equation. Does that mean that N2 is a constant? No. N1 is not necessarily a constant. It's not a constant. This is the approximate solution. So those of you who are in Pilling's class, he talked about this early on, the steady state approximation. It's just a way to solve this little equation. This term is small, so let's just keep the two big ones. So this is an approximate solution, which is quite valid most of the time. The solution for N2, assuming steady state, is just N1 times the proportionality of these terms. Now you're beginning to see the problem. What's N1? That's the number density in the absorbing state. If you knew the temperature, you know the relationship of that N1 to the total density of that species, which is usually what you want. So if you know the temperature, this is just the Boltzmann fraction times the number density. The problem is here. Well, this is just the Einstein coefficient times I, Einstein coefficient. So that's not too much trouble. A is known, Q's the trouble. There's no fundamental value for Q. It's a quenching collision frequency. That's the problem. So the good news is we have a solution, and once you have N2, you can stick it into the equation and you immediately have the signal. Here's our equation for N2, repeated. And all I'd have to do, and here's my reminder to you that W is I times B. So the left-hand side, the right-hand side, and multiply by I have the same relationship of the W's. So my equation for signal, either in photons per second or in total photons, is get done once I know N2. So now I have an equation for N2, and I can put that back into the... And now it turns out that there are two interesting limits to solve this, to identify the value of this. One's called the weak excitation or linear regime. One's called the strong excitation or saturated regime, which has to do with the relative values of these terms in the denominator. We'll look at the weak excitation first. Weak excitation means that the induced emission from 2 is weaker than the other terms. So you need this one because that's the only way you get signal. This one you don't necessarily need. These are the removal terms. And it's okay if this one is smaller than these two. And when it is, I can replace that. So W21 is frequently smaller than A21 over Q21. And in that limit, we call it the weak excitation limit. Now that's kind of telling you that N2 is much smaller than N1, which is kind of intuitive. It's the upper state. So N2 is going to be smaller than N1. So in the limit that is really weak, I'm not going to depopulate N1 very much. So the approximate answer is N2 is the starting value of N1 times this very simple ratio. And remember, W is just IB. So there's an IB and an IB. Oh, no, I got rid of that one. There's an A and a Q down here. So I got an IB, an A, which the B's and the A's are related, and I got Q. So what you're going to see is Q's the problem. So let's look in the weak excitation limit. Here's our signal, back again, photons per second. Number density times the volume times A times omega over 4 pi. Now I'm going to insert my answer for N2, which is N1 here, times W12 divided by A plus Q. So I've rearranged the terms because I like this format. This says that the signal is the photons absorbed per second times the fraction that re-emit times the fraction you collect. So it's just a product of terms. My success rate is how many photons I can get absorbed times the fraction I can get to emit. Because look at this. I'm excited, and where can it go? It can only decay by these two processes. What's the yield? It depends on the relative value of Q and A. If Q is small, every absorbed photon gives me one back. If Q is huge, it's the ratio of A over Q that comes into play. So we need to know something about Q21. But you can already see the signal is linearly proportional to the number of molecules in that state, the volume that you illuminate, the intensity of your laser, the fraction that you collect, and A over Q. So it's kind of simple. You can see the issue right in front of you. You can rearrange these terms and talk about this a different way. That's in the notes. You can puzzle through that if you want. But there's another limit that people explored for. So this Q problem was the bugaboo for a long time. How do you make fluorescence quantitative? You can get a signal, but what is it? It means the molecule's there, but how much? Depends on Q. And you want to know if you want to know this to within 10%, you've got to know Q to really well. So that's a problem. So people said, let's get rid of Q. Let's change things around so that W21 is bigger than these two. Crank up the laser. keep cranking it up until W21 is bigger than the sum of these two. The units are always per second, so I just crank up this laser until it's bigger than this term. In concept, you can do this. Then what? Then N2 is given by N1 times W12 over W21, which is the ratio of the B's, and N2 is N1 times the ratio of the degeneracies. If the ratio of the degeneracies is 1, N2 equals N1. And the sum, N1 plus N2, is N10. Very attractive. Very attractive. That's called saturation. That means you take the molecules and you pump it up to the point that the decay process is equal to the absorption. They're equal. They just keep its dynamic equilibrium. So in the limit that there's only two levels, N10 is the sum of N1 and N2, then N2 is the signal, the thing you're after, divided by 1 plus the ratio. So in the limit that the G's are equal, N2 is just the initial value divided by 2. And again, if you knew the temperature, you'd know how many molecules were in that, what fraction of the molecules were in that state, and you'd be done. Looks very attractive. So people have studied this a lot. The saturation limit gives you a way to get around Q. So it doesn't depend on Q anymore. Complication is you may not be able to saturate in a combustor at atmospheric pressure. You may not be able to do this. Or maybe if your beam has a Gaussian energy distribution, part of the illumination volume is saturated and part isn't. And you're looking at that and it could get a little dicey. Nonetheless, a lot of people try to do this. So frequently you're in the intermediate regime. And I'm going to just show you the equations and then move on. It's in the notes. Let's see here. You can solve the same problem recognizing that you can no longer throw out a term. And when you do, you can plot the signal divided by its saturation value so that it asymptotes to 1 versus the basically laser intensity out here. And you can, so when the intensity is wimpy, you get a linear result. When the intensity is saturated, you get this answer. So you can get more signal and be independent of Q if you saturate. If you're in between, you've got to do a solution which still depends on Q. So you really don't want to be in between. You either want to be one limit or the other, independent of Q or in the linear regime. But the math is kind of straightforward. So let's look at some typical values to see where we might be. Let's assume we're looking at electronic transitions for something like NO or OH, where the Einstein A coefficient has a value of like 10 to the 6th or so. 10 to the 5 to 10 to the 6th. That means the average lifetime is 10 to the minus 5 to 10 to the minus 6 seconds. If we were doing atoms, which have bigger oscillator strengths, you can get up to like 10 to the 8th per second. That's because that oscillator strength is probably around 0.3 or 0.4. Now we also have to look at Q. What's Q? Q is basically a collision frequency. It's the quenching collision frequency, which is nearly the collision frequency. We can write that in terms of a number density and the cross-sectional area and a mean molecular velocity. And you can look at that and see that it scales with the cross-section P over root T. Roughly speaking, this is the collision frequency, which is in the range of 10 to the 9th to 10 to the 10th for standard pressure and temperature. Scales like P over T. So Q goes up with with P, and it declines as 1 over root T when temperature goes up. So if you go from 300 degrees to 1200 degrees, it's going to go down by 2. But if you do this at high pressures, it's going to go up linearly. So that's the size of the number. That's the number you have to beat. You have to beat Q. So A over Q, what do we look? If we take one of these A's, let's say 10 to the 6th. Take 10 to the 6th, Reno. Let's take Q of 10 to the 9th. I get 10 to the minus 3. It's pretty obvious I'm not saturating. So If you look at this another way, the fluorescence yield, which would be A over the sum of these two, now say, because I've only left out the induced emission term, so I'm down in the weaker limit. All this says is that since A over Q is small, I can forget the A over Q is very small. That means LIF is a very inefficient process. So if you think about photons out is photons in times fraction absorbed times fraction that re-emit times the fraction you collect. If the fraction that you re-emit, which is called the quantum yield or the fluorescence quantum yield, is small, that's this number, 10 to the minus 3. And if I'm only going to collect omega over 4 pi, 1%, I've already got a 10 to the minus 5 in this problem. Photons in, or photons out, is photons in, fraction collected in measurement volume V, times 10 to the minus 5. I want photons out. I better send in a lot of photons. So people send in 10 to the 19th photons. Now we've got big numbers. Okay, so that's the game. You beat this game by sending in lots of photons, trying maybe usually to stay in the linear regime, and somehow figuring out what Q is. But you'll get signal. And so you can detect the presence of something. Now the game is can you make it quantitative? Okay, looks like I'm continuing now. If we want to translate this to, if I want to saturate, okay, I'm going to get rid of Q, I'm going to saturate. How many photons do I have to send in? So what is the intensity in order for B21 I nu to be greater than the other two terms in the denominator? Let's call that ISAT. Let's do this now for the case where Q is small, so I just have to worry about A. Then ISAT has to be greater than this, and I can also do it for high Q where ISAT has to be greater than Q over B. These are two limits. If you look at the equations that are in my notes for how you relate B to A and so on, and you pick a wavelength and you pick some reasonable numbers like 500 nanometers, you can show that in my units, B21 is 25 times A21 if you have B in these units. So B is about 25A. Now if we assume that Q is 10 to the fourth A, which is, remember a minute ago we had A over Q is 10 to the minus 3, 10 to the minus 4. So if we assume Q is about 10 to the fourth A, and if we assume that A is about 10 to the 6th, which it would be for NO or OH, actually I think OH is about 10 to the 5th. That says that this saturation intensity, which has units of watts per square centimeter per unit frequency, usually, I can put in the numbers, and what do I get? I end up with 0.4 joules per square meter, or 400 ergs per square centimeter. That's hard to deal with that, so we'll switch it over to say, I think we're going to do this in terms of power. But I can represent the intensity as the power of my laser divided by an area in some sort of a frequency width. And I think I'll just kind of skip, if you do it that way, now solve for power, in order to saturate, you get 5 kilowatts. So if I had a 5 kilowatt laser that would run for, say, some nanoseconds maybe, and I focus it down to spot size of about 1 millimeter, and I collected the amount of light that we typically collect, 5 kilowatts might do the job for a 2-level oscillator. So if the molecule had just 2 levels, and with representative values of A and Q, atmospheric pressure, I just have to have 5 kilowatts. And now maybe you're not now so sure that you can do this. I'm talking about milliwatts yesterday of absorption, and now we're talking kilowatts here. Okay, sounds like it's way too high for CW laser. But if you use a neodymium YAG pump dye laser of modest capability, it can emit typically millijoules, maybe tens of millijoules, even in the UV with OH. So typically to do a successful PLIF experiment, you'd like to have 1 to 2 millijoules. The high repetition rate boys are doing this, or people are doing this with 0.1, 0.2, 0.3. Not looking so good in the signals, but anyway, if you use a kind of a modest system, and I calculate the power, all of a sudden it's looking attractive again. Hold it, the instantaneous power is a megawatt. I think it's true that when the Livermore laser goes off, it's kind of like way more than all the power in the world, but just for, you know, some very, very small part of the time. So you spend a lot of time charging up your capacitors or whatever, and then you dump it in sub, you know, short time. So within the limits of a two-level model, which you can reach with an atom, you can saturate. So you're back to saying, maybe I can solve this problem. But molecules is a tricky problem because molecules are not really two-level systems. Every time I depopulate level J, the neighbors want to come in and repopulate at a rate of 10 to the 9, 10 to the 10. So every time I bump some up here, trying to saturate, the neighbors come in. It's really hard to achieve, to get these levels equal. It's really hard to saturate. So it's not so easy. Most people in combustion problems, where you're typically at atmospheric pressure or higher, don't do this. But you could in, say, a low pressure problem, a plasma problem of some kind. There's still some potential to this if you can overcome some of the problems. Okay, let's see. I think this, I was going to say back here. Oh, so what could we gain maybe by thinking about doing this in the infrared? So one point in my career, somebody came to me and said, would you like some money? And the Navy guy, and I said yes. And so I tried to come up with some great idea, and so I decided we should try infrared PLIF. Nobody had ever tried infrared PLIF. Usually you don't do infrared PLIF because the Einstein A coefficient for CO, I told you, is how big? Fundamental transition of CO, how big is A? 30. Not 10 to the 5th, not 10 to the 6th, it's 30. 3 times 10 to the 1. So the average lifetime of CO in the absence of a collision is the 30 milliseconds. A is so small that A over Q must be terrible. Until you stop and think, hold it, I'm not sure I know what Q is anymore. It's not an electronic quenching collision. It's an energy transfer collision. We better stop and think about this. So we did. And so we tried this for CO, delta V of 1. And now you have to decide what Q21 is. Is it the vibration translation transfer rate to get you back to where you were? There's no electronic collision. And so it's usually what's called VV. It's usually when a molecule of CO hits a molecule and it transfers its vibrational quantum out that way. That's a loss process. It means it can't emit. You've lost it. That number might only be 10 to the 5th. So the fluorescent yield, when you look at it that way, might actually be in the same range that we were talking about. That was like a revelation to me to think about this. So let's see, where am I here? Look, I think my slides are out of order or something. I think that slide shouldn't have been there. So I must have gone, oh, I know. I want to talk now about it's a little out of sequence. I want to talk now not about the infrared, but I want to talk about the detection limits. So you might have said, well, we got weak excitation, saturation. What kind of mole fractions could we detect? So our signal is going to be some sort of time integral over the pulse length. We're going to have to use a pulse laser. So we're going to have to integrate the signal over time. You have to put in the expression for N2 of time, which is now this constant which comes out. And you have to consider the laser pulse energy and the laser line width to get the, because remember it's watts per square centimeter per unit frequency. Cross-sectional area, you've got to put in some terms. And so here's our equation for the signal, for what we're after, the length of the measurement volume. Where did I get that? There was a volume, yeah, but I got to have laser power per area. So when you work that out, you're left with just the length. This is the energy in the pulse energy, because usually they'll say, how many millijoules do you have? That's the pulse energy. What's the laser line width? That's there. What's the B coefficient? A over Q. So in the limited A over Q, this is our answer for the signal. And if we put in some numbers, this is in your reader, so I'll just kind of go through it. You put in some typical numbers like, say, what did I do? I did this for 10 microjoules. That's a pretty small number. Typical pulse length, well, it's not typical, but 10 nanoseconds. Laser line width, number density at 1 atmosphere, 1600. Boltzmann fraction, 1%. I think we did an example where we calculated the Boltzmann fraction in one state and we got like 2%. Take 1%. Measurement volume, say, millimeter by millimeter by millimeter, 10 to the minus 3 cubic centimeters. Collection angle, 10 to the minus 3, let's be conservative. Einstein coefficients, put those things in. The detection limit, or the signal is 3 times 10 to the 7th times chi. Chi is the mole fraction. That's the signal in photons. It would be 3 times 10 to the 7th times the mole fraction. So if the mole fraction is 1 ppm, 10 to the minus 6, that's 30. 30 photons. I still haven't converted the photons to electrons. So now you have to introduce the quantum efficiency of converting the photons to photoelectrons. And that's the number where the photons come in and you get an electron and you collect it. And you can show, or you can read about from somebody who can show that when you have shot noise limited detection, Poisson statistics, that the so-called signal noise ratio is the number of photons times the quantum efficiency square root. So now I got a square root, and I'm going to take a quantum efficiency of 0.1, I guess. What's the signal noise ratio? It's 1.7 for 1 ppm. Now this is looking pretty good again. That's just why people like fluorescence. Modest laser, modest conditions, you can detect parts per million. And you now have a sense as to how is this going to vary with intensity, with partial pressure, with temperature. So you can detect photons. You can detect 10 photons with you can detect small numbers of photons. I'm not yet quantitative. Not yet quantitative, but I'm getting close. If you do this in the saturation limit, the equations change a little bit, and you can work your way through it, and you pick up another gain. So in fact, signal noise ratio is 5 for 1 ppm. Detection limit is like 40 parts per billion. So if you can saturate, most likely for an atom, not for a molecule, if you can saturate, you can detect parts per billion. Now it assumes you don't have some big problem with interference emission or something, but this gets people excited. The analytical chemists get excited by this. Somebody asked about transients. So let's talk about the characteristic times in this problem. We go back to our equation for the signal. This is, if you tell me n2 of time, I can tell you the signal in time using my steady state argument. So here's the steady state value, steady state solution. And the question is, do I have to worry about the time it takes to reach steady state? So I've used steady state. How long do I have to wait before steady state applies? That's the question. So you go through this, and you'd have to read it again to go through this. You can go through this analysis. So these are the limits for N2 in the steady state. This is the equation for the weak limit right here. Excuse me. So the way I define characteristic time, and I think it's exactly this way Professor Pilling does it. You can define a characteristic time by the ultimate value in the initial rate of production. We call this N2 final, the steady state value, divided by the initial rate of production. That's a characteristic time. It's not, it's just a number that reflects this time. So this steady state then is basically just 1 over this removal term, which usually these W's are smaller, so it's going to be something like 1 over Q. What happens when I turn the pulse off? Steady state goes away. And it has a decay time that is only A plus Q because there's no longer any more W's. So, 2 cases, weak and strong. In the case where we have weak, W12 is small, some typical numbers. Q is in the range 10 to the 9th, 10 to the 10th. It's good for once you hit, say, 0.1, 0.2, 0.3 nanoseconds. So if you're comfortable with working with nanoseconds and longer, you can use steady state analysis. If you're one of these people, no, I want to do femtosecond fluorescence, you're going to have to change your analysis. You have to use the so-called density matrix approach. And it allows, basically, when a molecule goes up to an excited state, it doesn't just sit there. It kind of oscillates like an oscillating electric field, and gets a lot more complicated. So short pulse, which would be picoseconds, femtoseconds, sub-nanosecond, you have to at least be careful about this problem. Usually to do successful fluorescence in combustion, you need a lot of photons. So you're usually talking about nanosecond lasers. Okay, I want to talk just very briefly about the modification to the two-level model. And I'm going to go kind of fast because I want to stay roughly on time. It's in my notes. There's two limits always, saturated and weak. This is a repeat of stuff we've already done. There's two things you have to worry about probably. One is, what if you have a spectrally narrow laser that only illuminates part of the line, part of the absorption line? Then you have to worry about something called hole burning. And now is when you have to decide whether this is homogeneously broadened or inhomogeneous. So that's something you can get into. The physicists get into this because there's some things they can learn about molecules this way. We usually are not in this regime. But it's a reminder why sometimes people use the words homogeneous or inhomogeneous broadening. This is now relevant. Here's our two-level model with vibrational and rotational quantum numbers. Here we are. Now let's assume that this thing has the possibility of a P, Q, and R. I excite here. Let's call this the Q branch line. But it can come back at three colors. P, Q, and R. It's not limited to the same. This just populates the state. Now we use the selection rules to say where it can go. On the other hand, if I wait very long, a collision comes along and it changes the rotational or the vibrational quantum number or collisional equations. QEL takes me back home to this manifold. Q vibration takes me to another vibrational level. Q rot takes me to another rotational state. Now what do I do? Every time it goes to a new state, it has a chance to emit at three colors. So for about 10 to the minus 9th or 10 seconds, it sits there, and if it emits, fine. If it doesn't, it's on to a new place. It's got a new fresh chance. What's the chance? A over Q. But you have to recognize there's three colors, and there's the sequence of processes. And the question is, how does that affect our two-level modeling? And there's two limits that people care about. One is the so-called narrow band limit. They did this at Purdue for a while. So let's say that you excite here, and it emits P, Q, and R, and you collect only one. Maybe you collect this one. That's called narrowband detection. And then you have to go back and ask, well, okay, narrowband detection. Here's my equation for populating. Now I have to write my equation for removal. You have to write the rate equation for removal from the collection bandwidth. A few words, very subtle, very important. All of a sudden now, it's not just Q electronic. It's also Q rotation. It's also Q vibe. Q is the sum of the removal from the observed state. And if you're going to limit yourself to observing from here, by virtue of looking only at one color, you've just lost a lot of signal. But in the limit that Q rot is the biggest term, and you know what it is, it's now quantitative again, at the price of signal. I think it's better to have bigger signals with some uncertainty than no signal. So that's my point of view. So I would say, no, let's look at this in another limit. Let's look at this now and then you can go through this. The key point, and it's in the notes, is when you go through this equation, the Q down here is the sum of the Q's that remove you from being observed. So I'm going to avoid this problem by going to, did I show broadband? What happened to my broadband? A broadband collection. broadband collection. I open up my spectrometer or my filter and I say, I don't care if it comes from here or here. I don't care where it comes from, as long as I get it. I'm going to collect a lot more photons. I go back to the same equation. Now, what's the summation of Q? Q is then the sum of the Q's that take me away from the observed bandwidth. And if I collect all the emitted light, it's only Q electronic. So I get my signal back. And what you can show, I'm not going to have time to do this, I think. It's in my notes. I'm going to show you one thing and then I'll say a word about the light. So basically, you recover signal, but you still have to know Q electronic. This is an interesting plot. I think my friend Bob Luck did this. This is the plot of what you see from OHLIF in a 30 torr flame at 2 different times. So this is the, I remember I said there's the fluorescence spectrum and there's the excitation spectrum. This is the fluorescence spectrum. You pump it one color and what comes out? What comes out if you wait 4 nanoseconds is this group of lines. This is frequency here. If you wait a little longer, the distribution changes. Why? It's changing its quantum state. Spectrum that's allowed is changing. Even at 30 torr, it's changing J. So that means it happens. It happens. So they thought, well, they'll avoid this problem by just collecting one line, but at the price they pay is too heavy. You get no signal, unless you're going to signal average. So I came up with this little scheme to show that in the limit that you look temporarily for, here's the quenching rate, there's the collisional rotational rate, and there's A. So it's like a stepped procedure. The fluorescence quantum yield immediately is alpha. That's the ratio of A over the loss term. Remember, it's the removal from collection bandwidth. It's A over Q. But now it goes to another level. But as long as A over Q stays the same and you do the math, you end up with the fact that the ultimate outcome is just A over Q electronic. So we haven't added any more requirement for knowledge than we had before. So the nice thing about this 2-level model is, in the limit that the A's and Q's are about the same, collecting light for more states doesn't hurt you at all. Keeps the signal up. Doesn't require any more information. So I like that. Now there's one more thing. Other people came along and said, I still don't like this Q problem. What can we do? They came up with the scheme and said, well, what about predissociation? So Pilling talks about curve crossing. So here's the lower state of OH, here's the upper state of OH. There's something called curve crossing. If you pump this excited state to this level or so, on each oscillation it leaks out. So the effective Q now includes a new term called Q predissociation. And it turns out that that number is kind of independent of collisions. It's like just a number. It's basically a collision frequency across this well. So all of a sudden now I've got signal number density is W12, N1 over Q, where Q pre is a constant. So this is like great. What's the problem? Q pre is a constant and it's a big number. Therefore, your signal is weak again. So the good solutions usually have some shortcoming. So that's one, but nonetheless, let's see, I'm going to go back to that. Next lecture, I'm going to talk about PLF of small molecules, and the last lecture will be PLF of big molecules. And I mention this now because I came along and we decided we have to find a way to get more signal. Instead of measuring, and my fluid mechanics friends, their eyes glazed over when I talked about spectroscopy. So I realized we have to do something that they're interested in. We have to dumb it down, make it simple. They were smart in their own field. So we figured out a way to get signals of tracer molecules that are not OH. So you do an experiment where they study fluid mechanics and not so much combustion. And so there's another, and there we will use this Q predissociation or curve crossing again, but we're going to find out that we can score. So you have to find a way to get around the Q problem. Fluorescence is a great technique, sensitive, hard to make it quantitative. If you only want to know if it's there, no problem. If you want to know how much is there, got a problem. But we can get around it with these big molecule tracers I'm going to tell you about in the last hour. Okay, we'll take a break for 10 minutes or so.